Welcome to The Explainer. Today, we are digging into the fundamental rules that run the entire show, from your coffee getting cold to the universe itself expanding. Yup, we're talking about the laws of thermodynamics.
So let's start with a really simple question that actually gets at a deep universal truth. We all know this happens. We've seen it 1,000 times. But why? Why does change seem to have a one-way ticket? The answer, it turns out, is written into the cosmic rulebook that governs all energy and all change.
All right, here's our game plan. First, we got to get our language straight and define some key terms. Then we'll jump into the first law, which is basically the universe's rule on accounting. After that, we'll get into the weird and wonderful second law, which explains why everything tends to get, well, messy. And finally, we'll bring it all together with a powerful tool that lets us predict if something is even possible. Okay, before we can talk about the rules, we have to define the playing field. In thermodynamics, you have to draw a line in the sand, even if it's an imaginary one, between the thing you're actually studying and literally everything else.
So first up is the system. This is our main character. It's the specific thing we're focused on, whether that's a chemical reaction happening in a beaker, a car engine, or even a tiny living cell. It's the little piece of the universe we're putting under the microscope.
And everything else? The beaker, the lab, the planet, the galaxy, the entire rest of the universe that is not our system, we just call that the surroundings. System plus surroundings equals, well, everything. It's a really simple idea, but it's super powerful.
Now, these systems can interact with their surroundings in a few different ways. An open system, like your morning cup of joe, can exchange both energy, you can feel the heat coming off it, and matter, like the steam rising. A closed system, maybe a tightly capped water bottle, can still let heat in or out, but no water is going to spill. And then you have the holy grail, an isolated system, like a perfect thermos, that exchanges absolutely nothing.
All right, with our terms set, let's get to our first major rule. The first law of thermodynamics is basically the universe's golden rule of accounting. It's all about making sure the books are always balanced.
And this is it, right here. The total amount of energy in the universe is fixed. It's constant. You can't just make it out of nothing, and you can't just make it disappear. All you can do is change its form, like from the chemical energy in gasoline to the kinetic energy that moves your car.
So if we're going to be cosmic accountants, how do we keep track of it all? We measure something called a system's internal energy, which we label with an E. You can think of it as the system's total energy bank account. It's the sum of every bit of energy all its molecules have.
And just like any good accountant, we need to know if money's coming in or going out. It's the same for energy. If energy goes into our system, either as heat or as work being done on it, we call that a positive change. If energy leaves our system, it's a negative change. It's all about the system's point of view.
And this all gets wrapped up in one beautifully simple equation. The change in a system's internal energy, that's delta E, is just the heat, Q, you add to it, plus the work, W, you do on it, a perfect energy balance sheet.
But wait a second, here's the big question. The first law is great for accounting, but it doesn't actually answer our original question about the ice cube. It says energy has to be conserved, sure, but it doesn't say why heat flows from hot to cold. The first law would be perfectly happy with a glass of water sucking heat out of a warm room and turning into ice, but that just never happens. So, why not?
And this brings us to the second, and you could argue much more profound law. The second law of thermodynamics is what gives time an arrow. It's why things in the universe seem to happen on a one-way street.
Think about it. Some things just happen. Iron rusts. A smell spreads across a room. Heat flows from a hot stove to a cool pot. We call these spontaneous processes because they just have a natural drive to happen all by themselves with no outside help.
The secret ingredient to understanding all this is a concept called entropy, which we represent with an S. It sounds complicated, but you can really just think of it as a scientific word for messiness or randomness or disorder. A neat, organized bedroom has low entropy. A messy one has high entropy.
And this, right here, is the absolute core of the second law. For any spontaneous thing that happens, the total entropy of the entire universe, the system plus its surroundings, has to go up. It's not enough to just conserve energy. You have to create more disorder. This is why a room gets messy on its own, but it never, ever cleans itself. The universe just prefers chaos.
Okay, so we've got the first law saying energy is conserved, and the second law saying disorder always increases.
So how do we put those two powerful ideas together to actually predict if something is going to happen? Well, that brings us to the final tool in our kit. Enter our hero, a brilliant American scientist named J.W. Gibbs. He had a stroke of genius. He realized he could combine the energy change of the first law and the disorder change of the second law into one single master value that would be the ultimate decider.
He called this free energy, or G. It's basically the amount of energy in a system that's actually available and free to do something useful. And the change in this free energy, delta G, is a combination of the change in a system's heat, that's enthalpy, delta H, its change in disorder, that's entropy, delta S, all balanced against the temperature, T. And the rule he came up with is just beautiful in its simplicity. If the change in Gibbs free energy for a process is negative, it's a green light. The process is spontaneous. It's going to happen. If it's positive, nope, it's a no-go. And if it's zero, everything's perfectly balanced. The system is at equilibrium. Delta G gives the final verdict.
And this table here is where all just clicks into place. It's the aha moment. A process that gives off heat and gets more messy? That's a sure bet. It's always going to happen. But look at those last two rows. That's where you have a tug of war between energy and entropy. And you know what the tiebreaker is? Temperature. This is exactly why ice spontaneously melts when it's hot, but not when it's cold.
So there you have it. We now have the universe's rule book for change. We can combine energy and entropy to tell us what can happen and what will happen. But that leaves us with one last truly fascinating question to chew on. If the whole universe is on a one-way trip to total disorder, then how is it possible for something as stunningly ordered, complex, and beautiful as life to exist at all? That's a pretty deep one to think about.